Well, thank you everybody for joining us today. My name is Angeline Burks, and I had the pleasure of meeting several of you at the Greenbuild Conference and Expo in Phoenix last month. And we're pleased to invite you to enjoy this complimentary webinar that's going to go over some of the benefits and theory and applications of displacement ventilation. Because this is a live webinar, I just wanted to touch on some webinar protocol for a moment. I would appreciate it if everybody could please keep their phones set to mute. We will open the forum for discussions and Q&A at the conclusion of the presentation. And please be sure to announce yourself if you are going to make a contribution. I'd also like to take a moment to introduce the presenter today. Cameron Regier is a mechanical engineer, and he is an internal expert at Price on several different sustainable air distribution technologies, such as displacement ventilation, underfloor air distribution, and hydronic products. Cam has extensive experience in the field, visiting a variety of different building types. He provides technical support and gives applications guidance. This presentation was also put together by Julian Rimmer, who's our Senior Product Manager for Sustainable Technology. And not only is he an internal expert on these products, he also travels the world studying sustainable technologies and how they are applied in a variety of applications. So I'm going to pass the floor over to Cam to lead us through the presentation.
Thank you, Angeline. Greetings, everyone. Thank you for joining us. So today I'm going to be giving you an introduction to displacement ventilation. So we're going to be going over an overview of displacement ventilation, some of the theory and design considerations, some of the displacement products that are available, some of our engineering support, and our research center to give you an idea of the technical backing that we have behind our displacement and the variety of our sustainable and products that we have. And then we're going to open it up to Q&A if anyone has any questions or comments. So starting off with the history of displacement systems, displacement is not really a new technology. It's been utilized in Europe for 30 to 40 years at least. It had its origins in industrial facilities simply because it was a more effective way of removing contaminants as opposed to a mixed system. And it actually still remains the #1 choice for industrial facilities in the European market. In the 80s, they started to apply it to the commercial market, and now we're seeing it become popular in North America as well. Now, to review the two systems, starting off with our standard mixing system, we have 55-degree supply, typically through a ceiling diffuser, where we would have a high-velocity diffuser. And what it's going to do is it's going to mix the space. So what you're seeing in this picture is a CFD printout of a simulation done with a ceiling plaque diffuser. And basically you're seeing the temperature distribution across the room pretty well even. The only zones that are not around 74, 75 or room temperature is the area right at the exit of the slot and right at the return. Otherwise, the rest of the room is pretty well even temperature. Now what you're getting here is the diffuser is driving the air motion. So we're having diffuser exit velocity of a few 100 feet per minute at least, up to 1,000 feet per minute. Very high velocity and very rapid mixing. We're mixing up that room entirely. Now contrasting that is a displacement system where we have much warmer supply temperature, where we had 55 degrees with the mixed system. We have 65 to 68 degrees or even up to neutral to room temperature supply. And very low velocity. In this case, it's usually around 40 to 50 feet per minute from the diffuser face. So you see in the lower right-hand corner here, this is the diffuser. And the air is just spilling out of the diffuser. It's then traveling across the floor, and it's pulled towards the heat sources. So in this case, there's very little or no mixing in the space, and the heat sources are driving the air motion. So we're just trickling air into the room, and we're allowing the warm heat sources to pull the cool air towards them. Now the significant difference here, aside from the velocity, is that we're stratifying all of the heat and the contaminants at the ceiling level. you'll notice that there's a much different temperature pattern in the room. Whereas we saw with this room where the temperature or the color is pretty much even across the room, in the displacement system we're seeing a dark red near the ceiling, which is indicating return temperatures up into the 80 degrees. And along the floor or right at the exit of the diffuser, it's around 65 to 68 degrees. So there's significant stratification or temperature gradient across the room. Now what that does is traps all the heat at the ceiling, and it also traps contaminants there. And because we're not using high velocity diffusers in the ceiling, we're not mixing all those contaminants and all of that heat back down. So it's not only more efficient in terms of indoor air quality, it's more efficient in terms of cooling. A quick summary of benefits here. We're going to go into these at length a little bit later in the presentation, but it's a very flexible system simply because we're not blowing air into the room and we're not driving the room motion with high velocity diffusers. We're now allowing the heat sources to pull the air wherever it's required. Because of the stratification, we also get a significantly improved indoor air quality and thermal comfort as well because of the low velocity and the warmer supply temperatures. Again, because of the lower velocity, the systems are also much quieter, and there are also energy savings and things like LEED and CHIPS credits that can be obtained with displacement ventilation. So the common applications for displacement ventilation run pretty well across the board. We've seen major interest in schools, green schools and programs like that have really been driving a lot of demand. To date, we've probably done half of our business in displacement in schools. But there are a variety of other applications for displacement, things like healthcare, airports, large public spaces like that, halls or conference rooms. Pretty well any space can be applicable for displacement ventilation. There's very few instances where displacement cannot be applied. So to give you an idea of the job distribution across North America, really, this is a distribution of our projects to up until about early 2009. This slide was updated. So we have a very high concentration on the west coast simply because the climate is very temperate. They can take advantage of something called free cooling, which I'll get into a little bit later. Basically, the cooling demand is low, the humidity is low, so it favors warmer supply temperature, and they can be bringing in outdoor air or running their economizer for a lot more hours of the year. But there is a lot of interest still across a variety of states across the U.S., and a lot of interest in the Great Lakes regions. They have a lot of school programs going on there, very progressive states in Minnesota and Michigan, and also in the Northeast. The Southeast becomes a little bit trickier simply because of the high humidity and the high cooling demand. So in these cases, it just takes consideration of humidity, your entering air temperatures, as well as your building construction to control humidity. And we do have a few jobs in this area now since then that have been supplied with displacement ventilation. So what this video is showing is that heat sources are basically going to drive the air motion in the room. Now the diffuser in the corner is basically spilling air out. It's going to travel across the floor, and this panel is depicting a warm body or a person in the room. So you can see how the cool air is moving up across the body. It's cooling the person or the piece of equipment or whatever this may be. And it's also delivering fresh, clean air right to the breathing zone. And you notice that smoke isn't being mixed back down, and it's not being mixed around the room. It's basically stratifying at the top of the room, and it's being pulled out by the returns. Now, thermal plumes are something that's created when we allow free convection, and that just means we're allowing bodies or warm bodies to sit in the room, and we're allowing heat to rise off the top of their heads. That's the simplest way to put it. What they do is create temperature stratification. So as heat rises off the top of your head or off a piece of equipment or a computer, it rises straight up because it's less dense than the room air, and then it's stratified at the ceiling. And what that's also doing is carrying contaminants away from the breathing zone. So as you breathe out CO2 and other contaminants, it's going to be carried up in your warm breath as well as that thermal plume, and it's going to be carried to the ceiling and stratified there. What that obviously does is improves the air quality in the occupied zone. If you remember back to the mixing case, we would have a diffuser in the ceiling that would be mixing all of that air back down into the occupied zone. So anything that someone is breathing on one side of the room is basically going to be mixed back down into the occupied zone to someone on the other side of the room. Now, one of the common concerns or questions with displacement ventilation is layout and furniture layout or complex geometry rooms or obstructions and things like that. With the air flowing along the floor, people are concerned that a desk or a chair or even a bookcase or something like that is going to block the flow, and one area of the room is not going to be conditioned properly. Now, what you can see from the video here is the air has been introduced from that corner diffuser. It's spilling across the floor. The mannequins are heated, so you'll see it start to develop thermal plumes around the mannequins. And it's spreading all the way across the floor into the far corner of this room, just from that corner diffuser. So even it's going around the desk, around all the objects in the room, and you can see it start to pull the smoke up the warm mannequin. So the layout is far more simple with the displacement ventilation system. I mentioned the air quality can be increased significantly with displacement ventilation. It is a more efficient contaminant removal method simply because we're not diluting the contaminants in the room. We're actually just stratifying, removing them from the breathing zone altogether, and then pulling them out through the returns, which is exactly what we want to do. ASHRAE 62, the standard for ventilation, or ventilation rate and indoor air quality, actually gives you a ventilation discount. So with a mixed system, the best case that you can get is a ventilation effectiveness of 1, which means the concentrations at the return, or concentration of any contaminant or any measure at the return over the concentration at the breathing zone is equal to 1, meaning the room is entirely mixed, and with a mixed system you really can't do any better than that. Now with the displacement system, because we can now stratify those contaminants away from the occupied zone, we can actually get a 20% better ventilation effectiveness. And now if you're doing your outdoor air requirements per ASHRAE 62, you can actually get an outdoor air requirement discount, so that you take your outdoor air requirement based on the number of people in the room and the square footage, and you divide that by 1.2, so you're really saving around 17% on the outdoor air. Because it bears mention, there's a significant benefits of increased indoor air quality. The two graphs on the side are depicting various studies done showing the benefits of increased ventilation effectiveness. Anywhere from about a 23% reduction in asthma, 47% reduction in sick building syndrome, up to 85% reduction in colds and flu transmission, things like that. And this is all in systems that have had improved ventilation effectiveness, higher than the standard mixed system. Now those benefits are obviously pretty significant as far as productivity goes, sick days and things like that. The other part is the Collaborative for High Performance Schools in the US has actually done studies that show that for schools with increased ventilation effectiveness, you see less sick days, so the kids are in school more. The divisions are paying less substitutes, so they are saving money in that case. Parents are home less, obviously sick with their kids, and they're seeing increased test scores because the kids have a better learning environment. And the final point to make on indoor air quality is that there is a LEED credit available for an increased ventilation rate, and because of the ventilation discount that I discussed earlier, it's actually easier to get that credit with a displacement ventilation system than it would be with a mixed system. Now a quick discussion on some of our research in indoor air quality in healthcare. What we've seen is reduced transmission, and the exposure is reduced for a person entering a patient room. So the two graphs on the bottom here are showing a sneeze. So a person is, in this case, a mannequin is lying in the bed, and this mannequin we've simulated a sneeze, and the measurement is taken at the caregiver's breathing zone, which is standing right beside the bed. So the one on the left is with the person sneezing towards them, and the one on the right is with the person sneezing up in the air. So if you take a look at the area under the curve, that's really the exposure. So if you're looking at this from the caregiver's point of view, you're seeing that they're exposed to a lot less contaminants, and things like transmission throughout the hospital, or even making that person sick or that caregiver sick, things like that are significantly reduced. Now, another thing that we're seeing a distinct advantage for displacement ventilation in healthcare is that the AIA and the FGI Facilities Guidelines Index is now recognizing displacement ventilation as far as the air changes in the occupied zone only. So if you're looking at a patient room or a waiting room area, and you have to have your 4 or your 6 air changes per hour, with a displacement system, they're now allowing you to do that calculation with the volume of the occupied zone, which is only the 6-foot height, instead of the 9 or 10-foot ceiling height, or whatever it may be, with a standard mix system. So the discount there with air delivery, the volume of air that you have to deliver is quite significant. Another question with displacement ventilation is, with the cool air moving along the floor, what about thermal comfort for people who are in shorts or skirts or open-toed shoes and things like that? So the first point is that the supply air temperature is actually much warmer than we are used to with traditional air conditioning systems. Whereas a traditional system, we would be using 55-degree air. With a displacement system, we're using 10-degree warmer air, about 65 degrees. So it's not far from room temperature. The other point is the velocity is significantly reduced. 40 feet per minute is barely perceptible. You can really have your hand up to these diffusers and move them 2 to 3 inches away, and you really don't feel any velocity. So with those two things in mind, you can still maintain comfort for pretty well anyone in the room, as long as you maintain these two guidelines of maintaining a supply temperature around 65 degrees and maintaining a face velocity or room velocity of around 40 feet per minute. And the final point out of the ASHRAE standard 55 is that we want to limit stratification to 5 degrees head to foot for a stratified system. So that means the temperature difference between your head and your feet should not exceed 5 degrees, and that's simply because ASHRAE feels that once it exceeds 5 degrees, people are going to start to feel that their feet are cooler than their head, and they're going to start to feel uncomfortable. There's obviously calculation methods and things for trying to calculate this in a system. We actually have software that can help you predict this head-to-foot temperature, and also help you predict the supply temperatures and supply volumes that will help you stay within these guidelines. Now, I mentioned energy savings and the popularity of displacement ventilation on the West Coast, and that's mainly due to free cooling. Free cooling is just a term that means basically you're able to pull in outdoor air and use it to cool your building. Whereas with a mixed system where you're using 55-degree air, there's really a limited amount of time of the year that you could be pulling in air where it's 55 degrees. With a displacement system, if you're looking at places like California, Washington, and Oregon, they have a significant portion of the year where they're able to run the economizer, just be pulling in outdoor air and not be using any mechanical cooling. So the increases or the reduction in energy usage is significant for those areas. Moving across the U.S., the rest of the U.S. is basically in the area that we consider significant. So these are there's probably significant potential in the shoulder seasons and portions of the year where they can still be pulling in a significant amount of, or using the economizer for a significant amount of hours. Again, as I mentioned, in the southeast where the humidity is very high and the cooling load is very high as well, the potential for free cooling is pretty minimal, simply because the dew point temperature is just much warmer than it's comfortable to supply. Other energy savings that are available with the displacement system are there is a potential for reduced air volumes, and this is mainly in spaces where you would see high ceilings. So because displacement conditions the occupied zone only, which is that lower 6 feet of the room, if you're looking at a room like a school gym or an auditorium, theater, something like that with a very high ceiling, you're actually only conditioning or concerned about conditioning the lower 6 to 7 feet of the room. So the air volume above that doesn't really need to be conditioned. And you can actually see a reduction in air volumes required to cool the room. This can be more significant if you're looking at something like a theater with very intense stage lighting. The convective load associated with all of that lighting is really not attributed to the occupied zone only, and you're just concerned about the radiant portion that falls into the occupied zone. So there's a significant portion there that really doesn't need to be conditioned. It can just stratify and be pulled out by the returns. Now the other point here is there's a potential for increased chiller efficiency because you're shifting your operative band up. With a typical mixed system, you'd see a supply temperature of 55 degrees, so 55 degrees off your coil, and your return temperature is going to be around 74, 75 degrees. So you're seeing a 20 degree delta T there. If you look at the displacement system, we see a 65 degree supply temperature, but there's still about a 20 degree delta T where you see return temperatures of around 80, 85 degrees up to 90 degrees. So by shifting that up in the operative band, your coefficient of performance on the chiller is actually increased. And because of the potential for reduced air volumes and reduced static pressures, reduced velocities throughout the system, there is a potential for lower fan horsepower as well. So smaller equipment or reduced sizing of the fan equipment as well. I mentioned humidity a little bit in dew point temperature control. Humidity control is still necessary, and of course with a warmer supply temperature, if you're pulling in 65 or 68 degree air, in some cases that just isn't dehumidified enough, so further dehumidification is necessary. Now there are systems that obviously are control strategies that will allow you to chill down to 55 and reheat back up to 65 without wasting a significant amount of energy. Systems like a face and bypass or side stream bypass, where you can just bypass some of that warm return air, which is around 80 or 85 degrees up to 90 degrees, and mix that with your 55 degree off coil air and get your 65 degrees out. Other systems which in cases where you can't do return air mixing, so things like hospitals or labs, where it's got to be a straight shot through and out the room, energy recovery becomes very advantageous because you can take advantage of some of that sensible heat and reheat your supply air. Another common question is duct sizing. Because the velocity is reduced so significantly with the displacement system, a common question is that if the duct sizing has to be significantly increased, and is there a cost penalty for that? A simple answer is no. The sizing of a duct is really similar to a conventional system. Really, the majority of the equipment is very similar to a conventional system from the diffuser back. The velocity reduction is really just done at the diffuser because of an increased face area. The one recommendation we do make is that you enlarge ductwork about 3 to 5 duct diameters upstream of the inlet. So if you're doing a transition into the room, let's say for a corner or a wall diffuser, you want to do that maybe above the ceiling and give it 4 or 5 feet of enlarged ductwork to limit your inlet velocities to around 1,000 feet per minute, and that's just for noise concerns. I mentioned energy savings being a big driver. Things like LEED and CHIPS, which is the Collaborative for High Performance Schools, have been driving a lot of the popularity in displacement ventilation. CHIPS is a voluntary program similar to LEED, which is in effect across the U.S. Many states have adopted this as criteria for new construction or retrofit. Basically, they're a body that does research and things like that to determine the healthiest methods and the best practices to design schools. So they actually identify displacement ventilation as a system of choice because of the health benefits, because of the learning benefits, because of the reduced sick days and things like that. And they actually identify up to 4 points which are available simply for using displacement ventilation in the majority of the building. As well, there's the program, the LEAD program, which has a variety of credits that could be applied, or that displacement ventilation could be applied to. The first would be the energy efficiency, the increased ventilation rate. As I mentioned, there's a LEAD credit for increasing your ventilation rate 30% above ASHRAE 62. So if you're already getting almost a 20% discount with the displacement system, it's much cheaper to obtain that credit with a displacement system than it would be with a mixed system. Thermal comfort, design of a system with thermal comfort is also a credit, and personal control is the one that you can actually obtain simply by using our diffusers, because we have several diffusers which allow personal control, like the underfloor baskets, which allow you to modulate the flow based on your personal preference, as well as we have wall diffusers with control knobs, which would allow each person in a small office or something like that to modify their own personal environment. Now there's three sort of scenarios with displacement ventilation. The first is the one we've been talking about, where we have a cooling differential, where the supply temperature is significantly cooler than the room temperature, so about 2 to 10 degrees Fahrenheit. In this case, the cool air is more dense than room air, and it's going to sink to the floor and then travel across the floor and find the heat sources. If you're looking at supply temperatures close to room temperature or slightly above it, of about 5 degrees, the air is basically going to travel straight out from the diffuser at about a 90-degree pattern, and it's going to travel in sort of a wall across the room. It's not going to stick as tight to the floor because it isn't quite as dense, but you're still able to provide your ventilation requirements or a slight heating demand. Now the final scenario here is when you exceed that 5 degrees, and typically we don't recommend this scenario simply because that air now lacks the velocity to overcome buoyancy. So the warm supply air is going to be less dense than the room air, and it's just going to want to go straight up because it has very little velocity coming off of that diffuser to mix into the room. Typically, we don't recommend this scenario, but we're actually seeing some research coming out of ASHRAE, a fairly large study that showed that a displacement system can still actually provide better ventilation effectiveness than a mixed system can in heating. So we're looking into this, and we're seeing that this previous way of thinking, it may not be quite right. There are a variety of different scenarios or different products that you can use or combine with a displacement system to provide heating. Systems that work well are things like perimeter radiation, so perimeter fin tube. We can combine diffusers with radiant heat and things like that. We have diffusers with integrated heat, which you see in the bottom right corner. There's a larger perforated face for the displacement operation and cooling. And then once it flips into heating, the actuator is going to close off one part of the plenum and direct the warm air through a slot diffuser. We also can do things like radiant ceiling panels, which can provide a very comfortable environment in combination with a displacement system for a slight heating demand. And then there's fan coil units or other things that can provide heat as well. Now the air volume calculations are done a little bit differently with displacement ventilation, simply because we're considering the occupied zone only. We follow the ASHRAE design guide for displacement ventilation, and we've summarized that in our green catalog as well. This was based on a study, research study based on a variety of different rooms, different load densities, different types of rooms. The majority of them had around a 9-foot ceiling height, and what these air volume calculations are going to do is help you calculate your supplier volume, your supplier temperature, and the exhaust air temperature as well. So why the standard heat transfer equation doesn't apply? Standard heat transfer equation in its simplest form is just your air volume required is equal to the amount of heat you have in the room divided by the difference in temperature between the room temperature you intend to maintain and the supply temperature that you intend to supply. So the standard mixed system, you would see your heat load divided by 20 because you see a 55 degree supply temperature and around a 75 degree room temperature. If we were to redo these calculations with a 65 degree temperature, you would see your air volume double, which is not quite correct because, again, this equation applies only applies to a completely mixed room. And in displacement ventilation, we're only considering the occupied zone, which is that lower 6-foot zone. So there's three different portions of load that we're concerned with. The first is occupants and equipment. Now, occupants and equipment have a convective load. There's air or warm air rising off the top of our heads. And the majority of that, again, is going to be exhausted through thermal plumes simply because it's going to rise straight up without significantly mixing or warming the occupied zone. We also have a radiant load, but the majority of our main view factors are to the ceiling and the wall, and radiant heat transfer is very significantly based on view factor. And again, the ceiling and the wall both outside the occupied zone, so the majority of that load we're not concerned with as well. The second component to the loads is lighting. As I mentioned earlier, the convective load is pretty well entirely attributed to the upper zone and plenum, so all the lighting, all the convective load from lighting is basically staying at the ceiling. We're not mixing it back down as we would with a mixed system. And then we have the radiant load, which is split between the upper zone and the lower zone, and it's also split depending on view factors and the types of surfaces in the room. The final component of the loads are the solar and skin loads. So the majority of the solar load is actually entering the upper zone, and that's going to be exhausted through thermal plumes. And any solar that happens to fall on the floor is going to warm the floor, of course, but that's going to then radiate to the ceiling, which is, again, outside the occupied zone. So the majority of your heat transfer with solar and skin or solar loads is really falling outside the occupied zone. And the final point, skin loads are outside the occupied zone because we're typically not occupying that 1-foot zone directly beside the wall or the window. So what we're left with is around 30% of the occupant and equipment load falling in the occupied zone, about 13% of overhead lighting falling into the occupied zone, and about 19% of the conduction and radiation through the envelope and through windows falling into the occupied zone. So it's a significant reduction from the standard case where we would mix all of the heat load into the room. Now we actually have an air volume calculation software that helps to simplify these equations or to simplify the design procedure. We have a beta version which is available right now. You can contact us for the link. And we also have a room layout tool which is due in 2009 or 2010, I should say, which is going to have significantly advanced features in here. We're going to have a room layout tool, so once you're done with the load calculations, you'll be able to pull out the software. You'll be able to start pulling and dragging and dropping diffusers into the room you create. It's going to show you what you're seeing here is the color gradients is showing you comfort curves in the room to show you how close you can place people to the diffusers. Sorry, I understand some people are not seeing the videos. In some cases, they don't show up. In any case, there were only two. There aren't any more videos. We have videos available on the website as well, available through our training modules as well as through the website. So if you wanted to see the video of the thermal plumes or the displacement air pattern, I can get you the link to the website, or you can find the videos on our multimedia center at price-hvac.com. So the final consideration with sizing and layout of diffusers is selecting a face velocity. So ASHRAE recommends a face velocity of around 40 feet per minute for optimal comfort. And basically all you have to do is take that CFM that you calculated through our software or through the design procedure that we lay out in our green catalog, and you divide by 40, which would get you your diffuser area that you require. From there, all you need to do is decide how many diffusers you want to place in the room, where you would like to place them. There's nothing to consider like throw or drop or collision of diffuser air streams. The layout is actually really simple, and as you saw from that smoke video, or you may have seen from the smoke video, the air just travels around the room. It kind of trickles along the floor and seeks out the heat sources. So furniture and strange geometry rooms aren't really much of a concern. So that selection of 40 feet per minute face velocity is based on a sedentary zone, which is something like an office or a classroom or something like that, where we would see people doing the majority of their activity sitting down, pretty light activity like office work or classroom. Now, transient areas where we see people moving around more, people working out in a fitness center or a gym, hallways or corridors or industrial spaces, they might appreciate a little bit higher velocity, and it's also going to save you on diffuser sizing and get you a little bit more cooling efficiency out of a single diffuser. So you can actually up the velocities. In some cases for industrial diffusers, we see face velocities 100 to 150 feet per minute. So to summarize the benefits of displacement ventilation before I move on with the products, we see a 20% greater ventilation effectiveness than a mixed system, and that's translating to a significantly reduced indoor or increased indoor air quality in the occupied zone. Again, we see superior thermal comfort simply because we're using warmer supply temperature and lower velocity systems. We're allowing the cool air to find the heat sources, and it's really thermodynamic dependent on how much cooling that body requires. Systems are very quiet, and the green building movement is driving a lot of developments in displacement ventilation, and a lot of interest in things like LEED and CHIPS can be applied, as well as a variety of energy savings outside of the LEED program and the CHIPS programs. There's a variety of cost savings available with the displacement system. So now we'll move on to the displacement products. We carry a wide variety of standard displacement diffusers, ranging from wall or ceiling mounted, floor mounted. We have the heat cool models, as I mentioned earlier, and we also have the industrial models for some high impact applications or special applications as well. So to start off with our wall diffusers, we have the DF, which is displacement flat. We have the one-way or three-way. These diffusers would mount against the wall. We have the DF1W, which is a recessed wall diffuser, which would basically the entire plenum will fit within the wall, and the grill is nice and flush to the wall. And then we have some corner units like the DF1C and the DR90, as well as the DR180, which can fit against a wall or a column. So a few examples here. We have the DF1W in a commercial cafeteria. This is at the University of Illinois. You can see the diffuser is recessed into the wall. The plenum and everything is recessed in the wall, and the grill fits nice and flush with the wall. So they don't lose any floor space. They don't have to worry about the grill, people bumping into the grill, or any sharp corners or losing any floor space. We have the DF1C in the school classroom here, built into the side or the corner of the wall. And there's also a DF3F, which is a special diffuser that we offer, which is basically the combination of two 90-degree ends and a flat diffuser in the middle, just for a little bit more air volume. We also have a DF1C in our office building here, which is in one of the offices upstairs. As well as on top of this diffuser, we can provide the duct covers, which hide all the duct work and everything above there. But we can also paint them. In this case, we painted it to allow you to use it as a whiteboard. So in this office, they can use it as a whiteboard or a magnet board or something like that to make use of that space. We We have some DF1s here, which are recessed into the wall and actually hidden, so you can barely even tell that they are actually diffusers in there. We also have DF1W here, a typical size for a small office. So again, it's recessed, it's out of the way, you don't have to worry about bumping into it or losing any floor space. We also have some recessed wall or ceiling diffusers, which are the DF1R and the DF1L. Some pictures of these, some installations. This is actually the San Francisco Conservatory of Music. You'll see that along the front of the stage here is a curved DF1R, so the grille is curved to match the contour of the stage. It's a custom color selected by the architect, so we have a wide range of custom capabilities available. The grills are also all the way along the outside of the stage as well for the performers. And in an office meeting room, we have them all the way along the front of the room. This is a 1x4 version, so it integrates with a standard T-bar system, basically just a drop into the ceiling. A few more examples of the DF1R. Architects really seem to like these diffusers because they can integrate them with a variety of different molding or trim work or mill work and things like that. In this case, they put them into the walls and sort of hid them behind inside this millwork. In that cafeteria in the University of Illinois, we have them run underneath the benches of the cafeteria, as well as in this casino. The entire back wall here is acting as the plenum, and each grill is just snapped into place into the face of that plenum. We also have a few floor-mounted diffusers, such as the column-style 360s, the round floor diffusers, and the floor grill diffusers as well, which can be fan-assisted or plenum actuated as well. So this is a very custom application here at the San Jose Airport, where we have some 360s. The perf is actually a custom selection by the architect. It was selected to match the ceiling perforation pattern. We also did a custom dome cap selected by the architect and a custom mounting system. We also have the round floor diffusers, which I mentioned earlier. These diffusers, you can see they're placed right underneath the slot machine players. They're placed all the way around the gaming floor, as well as commonly in an office building or a call center or things like that, where they can actually be placed very close to people, within a couple feet of them basically, or in auditoriums where they can be placed right underneath the seats. For office buildings especially, these are the diffusers where you can order the basket, which can be individually modulated. Basically all you have to do is turn the face to get more or less flow out of them. So each person can have personal control of their little environment. A couple interesting architectural examples here. A DR360, which looks to be done in stainless steel with an integrated table and lighting on top, as well as a rounded DR180 in this cafe. Now we also have a variety of heat-cool diffusers, which is a new concept. We have the displacement with integral heater, where we have along the bottom is the displacement diffuser, so you have your cool, low-velocity air provided through the bottom of this, and there's a plenum on the back. And then on top you have your fin tube heater or your electric heater to provide your conditioning of the skin loads. So these are very popular for office buildings or for schools as well, where you have a lot of perimeter glass, a lot of perimeter wall to condition, and you need to provide the air volume as well for either ventilation in the winter or as well as cooling in the summer. We also have the changeover diffusers, which we've done a lot of development on in the last couple of years. You can see the depiction of the pattern here, where you have the larger perforated face active in the displacement mode or in the cooling mode. So the cool air just spills out of that diffuser. This diffuser is mounted in the ceiling. It's going to spill out of the diffuser and then travel across the floor. Once it's into heating mode, it gets a signal from either the BAS or the controls or the building controls. That's going to tell it that it's into heating mode to switch over that actuator close off the cooling plenum and open up the heating plenum, which is now going to direct all the warm air through that slot diffuser on the bottom. So that slot diffuser has a pattern control so that you can adjust it for a horizontal pattern or vertical pattern, so you can condition a window or a wall or something like that. A couple installation examples. You have a cafeteria again, where you see the cooling portion running along the bottom of this diffuser or this enclosure, and on top they have a dual row of fin tube, as well as here along the office building perimeter right along the glass. You have the fin tube on top and the displacement section on the bottom. We also carry a variety of industrial diffusers, starting off with the DR360, which is duct hung. So these can be ceiling mounted. We also have floor mounted diffusers like the DFX, and then a variety of Krantz products, which is a German manufacturer that we rep in the US. So some examples of installations. We have the duct hung diffusers here, which are in a manufacturing plant. Very large diffusers here for the specific application. You can see some DFX along this wall. So you can see they have a corrugated steel construction. They have mullions every 12 inches, so they're a very upgraded construction, suitable for high traffic areas like a manufacturing plant. In this case, this was a maintenance shop and a mechanical area, as well as things like a school gym or something where you're going to be concerned about kids running into them or hitting them with basketballs and stuff like that. We do have extensive custom options available, if that hasn't been apparent. So we have custom color possibilities, the possibility for perforation patterns. We work with architects very, very often to determine diffusers or come up with the diffusers that make both the architect and the engineer happy. So we can do things like custom material, custom fastening systems, and especially architectural integration, which we'll show a few examples of here. On the left, you see the Kirsch Center for Environmental Studies in California. In this case, there's a DF1W, which is that recessed diffuser, but it's actually curved to match the contour of the wall. So you see the larger perforated displacement face on top, and you see the heating grill running along the bottom. So they can do both operations with that one grill. As well, here's the San Jose airport again. This was during the construction phase, so each of these black holes in the wall is just a plenum waiting for a diffuser to be snapped in. So the diffusers here are along the wall. They had that same custom perforation, the same custom color, so that they basically just snapped into the wall. And they were about 5 feet wide by about 9 or 10 feet tall. So very, very custom size, entirely custom diffuser, and also a custom fastening system so that there were no visible fasteners as well. And again, these diffusers were significantly upgraded to be used for an airport as well, to be able to stand up to luggage carts banging into them and things like that. We also provided some column-wrapped diffusers here. You can see them in the school cafeteria. There's a condiment stand on top of that. And the kids are, again, sitting very close to these diffusers, so they can provide significantly improved thermal comfort even with people sitting within a couple feet of the diffuser. We also provided some hinged DR360s, so you can see the split line there, but basically these diffusers came in one piece. They snapped around the column, and all they had to do was duct from the top, and the entire unit was pressurized. So the active section is running along that lower portion. Actually, each of these columns has electrical service integrated into it as well, so each of those columns has a plug-in. We've also provided custom wall diffusers, which you see here. We have one of each of these in our US tech centers because we liked them so much the first time we built them for a customer. So you can see there's a DR180 hidden behind this custom grill, as well as DF1 hidden behind this grill, and it's all integrated into this nice wooden millwork. Some concepts we've worked on for displacement diffusers. We have a slot machine where we've integrated the displacement diffuser into the grill in the bottom. Some diffusers for an airport, planter diffusers with and without lights. Some of the specialty diffusers that we're working on or have worked on, we've provided lab diffusers where we had HEPA and ultrafiltration integrated. They had an ultra low sound requirement, so we can reduce the velocities as well as the vibration or the sound output. And we can also provide them with internal or external insulation. We've also launched the PureFlow patient room solution diffuser or patient room diffuser, which is just basically an upgraded diffuser. Whoops, excuse me. So the PureFlow hospital diffuser has a removable face, things like tamper-proof fasteners so that the cleaning staff can get in there to remove them, to remove the faces and clean them out, but anyone else can't get in there. And then there's a stainless steel option as well for intense cleaning applications. Now, as far as our manufacturing go, we do manufacture in North America. We have a standard 5-week lead time, and we have that custom capability. If you look at our competitors, the majority of them are in Europe, and their lead times are going to be at least double, if not triple that, to get their diffusers here. And their custom capabilities are not going to be quite as good. We also have a knowledgeable applications team here, which I'm part of. We can provide application support, technical training. We can bring groups in, bring your project teams in with the owners, the architects, the engineers to provide training or mock-ups. We can do we do a variety of research here at our research center as well as our tech centers in the US. Some of the resources available for displacement ventilation, we have the green catalog and design guide as well as our training module on our website. We have our product brochures, which are available through your price rep, which are our displacement products brochure, our schools brochure, and we also have a critical environments brochure, which has a displacement section in it as well. And we also have the air volume calculation software, which can help an engineer if they're trying to design a displacement system. What's forthcoming for displacement resources? We have an expanded design guide coming up with probably at least 50% of the content increased. We have a number of new examples and the combination of things like radiant panels or hydronic products with displacement. We're also looking at a healthcare design guide and a schools design guide. And as I mentioned, the closest thing is going to be that selection software that will be coming out in 2010, which will allow you to basically lay out a whole room and drag and drop diffusers into the room and allow you to accurately predict comfort. CFD is another useful tool that we utilize. We started off using this just for product development to help us reduce the wait times in the lab, but we've seen it as a significant area to help us grow our product lines. Especially with the sustainable products, which people are less comfortable with the displacement products, the UFAD products, and the hydronic products. Basically what we can do is we can take the room loads, we can take the room layout, and then we can simulate the system performance. We can get a variety of outputs like temperature, velocity, thermal comfort, indoor air quality, all things that the engineer and the owner might be concerned with. We can also use this for system optimization, where we can provide a couple different layouts, or we can go with the engineer's first layout and see how that works, and in some cases we're able to improve on that based on the flow patterns within the room. So this is a CFD study that we did for a hospital in California, where they wanted to compare the two pertinent things, thermal comfort and ventilation effectiveness in a hospital patient room. So what you see is two visitors in the room and one person in the patient bed. And on the left, unfortunately my diagram or my tags aren't showing up, but on the left is the mixed system and on the right is the displacement system. So if we look at the ventilation effectiveness of the mixed system, we see ventilation effectiveness pretty well even across the room. It's around 0.7, 0.8, and again, not really 1, which ASHRAE says it could be. The only region where it's really much higher than 1 is right around the diffuser, obviously, because that's where the fresh air supply is. But the rest of the room is pretty well fully mixed, so we see the contaminants even throughout the room, which is not great for either if this person in the bed happens to have a compromised immune system, or someone else in the room is sick, or this person in the bed has something contagious that they don't want to be passing to other people in the room. Basically, that mixing diffuser in the ceiling is mixing everything around the room. So everything that one person is breathing, the other 2 people in the room are breathing as well. If we look at ventilation effectiveness for the displacement case, we see that dark blue area, which is actually depicting ventilation effectiveness of around 2.25 to 2.5. So it's 2.5 times cleaner than at the return level, which means the contaminants are basically being effectively removed from the occupied zone and not mixed back down. And you can see the flow patterns that the thermal plumes are creating, providing that fresh breathing zone or fresh air zone right around the breathing zone. And the most contaminated area is right at the ceiling, which is exactly what we want, so that whatever each person is breathing out is being carried right to the ceiling and it's not being mixed back down to anyone else in the room. If we take a look at the thermal comfort printout here, you can see that high velocity ceiling diffuser is throwing air across the ceiling. In some cases it's extending down the wall with significant velocity, and then down along the floor actually. So the red is showing 30% PPD, which is a measurement of draft. So this is 30% people are predicted to be dissatisfied in that red region. So that's extending all the way up around this one person. The zone around the person in the bed is still only around 10 to 15, which is not bad. But if you look at all the visitors, it's not a terribly comfortable environment. You're still seeing high velocities. And ASHRAE 55 says you should design a room to maintain 20% PPD. So maintaining 80% people satisfied in this room. And this room would not fit the bill. If we look at the displacement case, the majority of the room is pretty well in this blue or dark blue zone, which is indicating less than 8% PPD. And the dark blue is actually the 0 zone. So there is a significant portion of the room that's much less than 10% PPD, with the exception of this one zone along the floor, which is right adjacent to the diffuser, so that you're going to get some significantly lower temperatures in that zone, which could cause drafts. So that's just a guideline for the placement of displacement diffusers as well. So I mentioned CFD as a powerful tool. We can also do mock-ups. We've done a variety of mock-ups. We do a couple of these a month at least in each of our tech centers. And what they can do is also verify system performance, but allow a person to walk into the room. So if CFD is not enough to convince someone, we can simulate the design conditions and have them walk right into the room. We have 2 different mock-up rooms, and then we have mock-up rooms in our Atlanta facility as well. And we can simulate all the working conditions with a hot or cold wall. We have windows. We can modify the room layout to the design size. And we can use a variety of products as well. And this can also be used in conjunction with CFD modeling to give you a very powerful tool to really sell projects to the owner, or to help the engineer with a little bit more justification or backing on projects. So a couple different mock-ups we've done here. We have a classroom mock-up here where each of those cylinders is representing an ASHRAE standard person or child. And you see the displacement diffusers at the back of the classroom and the data tree, which is collecting results throughout the room. We did a church retrofit mock-up here, just some examples where we see underfloor diffusers placed right underneath the pews, and the owner wanted to see that the system was going to be comfortable, even with the diffusers only several inches away from the people's feet or from their legs. We've also done a variety of hospital mock-ups. We've done indoor air quality, where we inject a tracer gas and then we test, we compare two or three different systems and compare the ventilation effectiveness and the contaminant exposure, and how effective that technology or that air delivery system is at removing contaminants from the room or removing that tracer gas that we've injected. So moving into the summary here, displacement offers significant benefits, as I mentioned, to indoor air quality, which can translate into significant benefits like productivity, increased test scores for kids, reduced sick days. Thermal comfort is also a big one as far as productivity goes, and the overall health and happiness of occupants. And then there's, on the owner or the building side, there's a potential for energy savings as well. Things like increased economizer use, the reduced mechanical energy required. And we also offer diverse standard and custom diffusers available for our displacement products, and we're literally about 80% of our business comes from customs or specials. Really only 20% of our diffusers are supplied straight out of the catalog. So we have a diverse custom diffuser capability, and which is ever expanding, and we're happy to work on customs. And again, as I mentioned, we can help with the design and selection. We can do performance simulations and mock-ups or training visits and things like that, and we can provide basically support at every step along the way. So I am going to turn it over to open discussion if anyone had any questions.
Thanks, Cameron. If nobody has any questions, that concludes today's presentation. We appreciate your time. If you need any additional information, please go ahead and contact us. And we did also record the webinar if you have somebody in your office that you would like to share this with. As Cam mentioned, we have extensive resources available on our websites, from design guide information through to training modules that help depict concepts such as displacement and how they work that you can track through at your own pace. So I hope everybody has a pleasant afternoon. Thank you very much.